So, in the previous lectures, whatever we have discussed about that your capacitors, particularly on the shunt capacitors, that that how it affects actually, and we have also talked that effect of shunt capacitor, basically its effect is local rather than global, and primary objective of shunt capacitor is to your what you call to increase the reduce the power loss, and though not much, it improves the voltage profile of the network. Now, when we will come to that application of your capacitors to distribution system, so first what we will do, we will talk about little bit about series capacitors. Also in the distribution systems, the application of series capacitor is restricted due to various reasons. We will explain that, and but for high tension line you may have series capacitors, but you need to have lot of protection, different type of protection scheme for the series capacitors, and there are many other issues. But anyway, so first let us when we will come to this, so further we will discuss. So first some basic definition. Actually we will not talk about the construction and other thing of capacitors, but some general ideas. So first thing is the capacitor element, right. So as you know, an indivisible part of a capacitor consisting of electrodes separated by dielectric material, this you know, perhaps you might have seen in the laboratory also. And next is the capacitor unit. So an assembly of one or more capacitor elements in a single container with terminals brought out, this also you might have seen, right. Then capacitor segment, a single phase group of capacitor units with protection and control system, and capacitor module, a 3-phase group of capacitor segment. Now, whenever we talk about all this course, only we will talk about the application of capacitor in distribution system, only that particularly from the point of view of that how to incorporate in load flow studies, and what will be your voltage magnitude, and what will be the power loss, and regarding that energy saving due to capacitor placement, right. Suppose annual energy saving, that is beyond the scope of this course, because it will consume lot of time, and at the same time you need the help of computer. Without writing code, it is not possible to actually explain that how things are, but we will see that how the energy saving is possible using your shunt capacitor. It is not only that if you design shunt capacitor in a distribution system in such a fashion, such that I mean if you can plan that that all the reactive powers that actually load requires, plus the reactive power losses in the distribution network, if you think that we will place the shunt capacitor in the network in such a fashion, such that it will supply, that shunt capacitor will supply all the reactive power required by the load as well as the reactive power losses, then one can see that it will not draw any reactive power from the grid. In that case, power factor at the your substation can nearly be maintained unity, right. So that is also proper planning is required, such that it will not draw any reactive power from the grid, and not only it is helping the distribution network, if it draws I mean if it is not drawing reactive power from the grid, means that means that is all the reactive component of the current is supplied by the shunt capacitor, particularly for the distribution network. It means that grid also will be relieved, right, because in the grid also that current will be less in various branches. So in other way there will be reduction in power loss in the grid, but that is a total your complete study is required for that, and it is not easy to do that. But from general intuition, it helps actually both distribution network of course, at the same time it grids, right. So all these things I mean with the general thing, whatever it is possible to some extent, we will see that as much as it can be done from the classroom exercise point of view, but rest some of the things I will tell you that how one can do it in the your what you call using the code. So these are all the capacitor element or the basic thing. and capacitor bank is a total assembly of capacitor modules electrically connected to each other. So, these are capacitor bank. Actually, that your first let me tell you something, then something more I will tell, that power capacitors. So, if you look at a casual look, a capacitor seems to be a very simple and unsophisticated apparatus, that is two metal plates separated by dry electric insulating materials. So, it has no moving parts, it is a static device, but instead functions by being acted upon electric stress, right. So, in reality, however, a power capacitor is a highly technical and complex device, in that very thin dielectric materials and high electric stresses are involved, coupled with highly sophisticated processing technique. Actually, in reality, that I am talking about shunt capacitor, that actually in reality shunt capacitors actually you have a fixed type of shunt capacitor and switch type of shunt capacitor connected to the network. So, particularly fixed type of capacitors, it will remain connected to the system throughout the your what you call year of the your throughout the year, right. It is a fixed one, it will, but in addition to that, that is at a light load level. But when load level increases, suppose if you consider a variation of load throughout a day, there will be a peak load, then off peak load, and between some medium load, right. So, all this at different load level, suppose your light load level out of 24 hours, suppose 10 to 12 hours if it is happening the light load level. So, you have to first determine what is the your capacitor optimized value at the light load level, and that can be treated as a fixed capacitor which will remain connected to the system all through the year. But and any load further increase, that additional capacitor bank will automatically connected at various load level. While load later I will try to explain you something such that those can be treated as a switch capacitor, and it switch capacitor as a different your what you call that switch on and off, that technique is different. One is that where it is connected, if you see the voltage level has gone below a certain magnitude of the voltage, then automatically capacitor will be switched on, right, and it will inject reactive power into the network. Another point is that if you use the time zone, if you know the load profile of the network, then you know from this time that switch capacitors will be switched on. So, automatically when that time will come, that capacitor bank will be your switched on, and it will again inject reactive power at that load level. So, that control technique is different. And another thing is that fixed capacitor is less expensive than switch capacitor. Switch capacitor is more expensive, at least 2.5 to 3 times whatever I know, right, and then because that control mechanism is there, because switch on and off. So, and another aspects of the capacitor is whatever we will study in this course, the capacitor we are treating as a constant power device, but in reality capacitor is a constant impedance type of element. That means that when it reacts your injects reactive power into the network, actually its magnitude actually directly proportional to the voltage square of the voltage magnitude. That means if at a rated value, if voltage is 1, it will inject the same var or kilovar or megavar into the network, that as per the manufacturer specification. But if voltage goes below 1, then as suppose it is 0.98 say. So, suppose your capacitor is say 500 kilovar, so it will be 500 into 0.98 square, right. So, it will inject less kilovar into the network. So, little bit will express that, but in the classroom point of view it is not possible using calculator to do that, but I will explain how things are. So, now first we will try about the series capacitor. So, generally as it is application of capacitor, that series capacitors used in distribution system is not much, it is restricted, but in transmission system that your what you call that many applications of series capacitors are there, but there you have before you are using series capacitor, you have to consider many other factors also. So, if you that is why series capacitor, that is capacitor connected in series with lines, have been used to a very limited extent on distribution circuit due to being a more sophisticated type of apparatus with a limited range of applications. Also, because of the special problems associated with each application, there is a requirement for a large amount of complex engineering investigations, because you have to consider one thing for series capacitor. From your general knowledge, the first thing is the resonance, right. So, many factors you have to consider, or I mean you have to consider many things. So, first, for example, if you consider this line, say simple line, say its impedance Z is given R plus Jx. This is actually figure 1AB, but two more figures are there in the next page, and this is the sending end voltage and this is the receiving end voltage, and there is your what you call no series capacitor here, but in the figure B here we have connected a series capacitor having reactance Xc. So, it is basically Z dash is equal to R plus J XL minus Xc. Xc is the reactance of the series capacitor. In a circuit theory problem, that series RLC circuit you have studied. You have studied also the resonance. So, for example, if your Xc become XL, so this part will be 0, reactive part will be 0. So, it will be at that time resonance will happen, but question is that you have because there are many other considerations. Generally, even if it is used that Xc should be less than equal to XL. If Xc greater than XL, it is overcompensation, right. So, little bit we will discuss series capacitor, not much, but your as far as theory is concerned will be explained here, but in the numerical type assignment we will give you some problem regarding a series capacitor. But this is sending end voltage, but this is receiving end voltage. As soon as you put this here, it is VR. So, I should make it VR dash, right, because as soon as you connect this one, so from your common sense you can make out this voltage drop will reduce. So, whenever you are see this is the current I, and this is your what you call that series capacitor, then what is will be reactive power? It will be basically magnitude I square into Xc, that is Qc, that is reactive power, that it is magnitude of I square into Xc for the series capacitor. Now, if the load changes, then this I mean it is something like this. All these things I have not written here, but suppose your Qc, that series capacitor, just hold on, that series capacitor's Qc, it is magnitude of I square into Xc. This is the reactive power from the series capacitor, right. So, if the load changes, this is the current I, some load is connected here, say. So, if load changes, it varies, it current, that means current can increase or decrease. So, if the current is decreasing, the Qc actually, if current is decreasing, Qc decreasing, because Xc remain constant, assuming that the frequency of the network remains constant. So, if the current decreases, then Qc will decrease. If current increases, Qc will increase. That means this Qc actually it is a variable thing. So, that means that means this series capacitor, what you can do is it is analogous to a voltage regulator, right. So, I mean that is sometimes we call boosting transformer. So, it is your there also that there is a possibility that your what you call so it is analogous of series capacitor. They say what that it is something like a voltage regulator. Later little bit we will talk about that, but so that means is Qc actually Xc remain constant, but because of changing I, that reactive power generated by the series capacitor actually it is changing. So, it acts like a voltage regulator. So, it is analogous to voltage regulator, right. So, if you draw the phasor diagram for this one, this is I, this current we are taking as a lagging current. For the leading current also we will see, but this is lagging current, right. So, corresponding to this diagram, figure A, this diagram, this is the phasor diagram. We have seen also for approximate voltage drop this thing. So, this is VR, right, and this current is lagging by an angle theta. This is actually this phasor is IR, this angle is theta, and this angle is 90 degree IXL, and this is the Vs. This portion is IR cos theta, this portion is IXL sin theta. This I have told you in that your what you call previously for approximate method approximate calculation in distribution system. And when you have here I have missed this one, this is VR, this is VR. So, when you are putting series capacitor means that here you look the if voltage drop, suppose the voltage drop in that your Iz dash is equal to it is I, then it is R plus J, it is XL minus XA, right. So, that means if you multiply this IR is okay, then it is J I XL minus j I x c. So, this from this one this is getting subtracted. So, that is why when you draw the phasor diagram for this one, this is actually your V r, this angle is theta, the current is lagging here, current is lagging theta. So, this is I r and this is I x l, that means your this part I x l, and this is minus your what you call I x c. This is not I c, it is it is actually I x c, right. So, this is I x c. So, this part, so you have to subtract. So, it take arrow downwards, or it is on the same line, but just to show you that how things are. So, this is actually I x c. So, and this voltage drop will be I z dash, and this is your new value, this is actually new value of your this thing, say V s dash, right. So, this is, that means here, and this angle is delta dash. Earlier it was delta, now it is delta dash. So, with that you will find delta dash actually it will decrease, because this V s actually is your V s dash actually is equal to V r plus I r cos theta plus I x l minus x c sin theta. So, this is the new position of the V s dash, right. So, that means your, if you place the series capacitor, right, if you place the series capacitor, so from that you can make out what will be the value of V s dash, because it is decreasing, because I into x c part is getting decreased, right. So, in that diagram. So, if you try to find out what will be your series capacitor, that approximate thing, then this angle is delta dash, same as before, right, same as before. If you make a horizontal line like this, and this distance is given, this distance is given. So, V s dash cos delta dash, that is your V s dash cos delta dash is equal to V r, this V r is equal to V r plus I r sin theta plus I r sin theta. When I am writing this I actually magnitude, right, magnitude, understandable, plus this part I into x l minus x c sin theta. So, I into x l minus x c sin theta, right. That means your V s dash cos delta is equal to V r plus I r sin theta plus I x l minus I x c plus I x l sin theta minus I x c sin theta, right. So, this delta dash actually it is smaller than also this one, previously we have made an approximation. So, this delta dash can be considered as too small, very small. That means you can write that if delta dash is very small, that means cosine delta dash approximately 1. That means you can write that equation V s dash is equal to V r plus I r sin theta plus I x l your sin theta, right. This much was already there, minus your I x c sin theta, right. That means earlier without series capacitor approximate thing was this was the approximate voltage drop. Now, this is the total, that means voltage drop is equal to actually I r sin theta plus I x l sin theta minus I x c sin theta. This voltage drop means that is equivalent to your voltage rise, right, because this much drop means that this much of voltage rise. So, that is your, this is your voltage drop equation. So, if we say that V s dash is equal to this one, this was without series capacitor, but not because of this much your what you call this much of minus I x c, it is sin theta, this much drop extra is there, it is subtracting from this one. So, this is actually voltage drop means this is equivalent to your what you call the voltage rise in the network. So, this is the approximate equation. So, in that means that is why your or not shown all these things, what I told you that voltage if voltage drop is getting reduced means the amount of reduction actually equivalent to the voltage rise, right, understandable. Now, therefore, as shown in figure 1, I told you that those figure 1, a series capacitor compensates for inductive reactance because it is x l minus x c, right, that is why it is compensating. In other words, a series capacitor is a negative your reactance in series with the circuit with positive reactance. But negative reactance means it is capacitive, positive means it is inductive, with the effect of compensating the part or all of it. I told you, right. So, if all of it means that your XL minus XC, it will be resonance condition, right. Therefore, the primary effect of the series capacitor is to minimize or even suppress the voltage drop caused by the inductive reactance in the circuit. So, what we are doing using series capacitor actually it reduces the voltage drop in the line. Naturally, that means it is helping to your what you call the voltage increase in the network, right. But at times series capacitor can even be considered as a voltage regulator, I told you, because that provides for a voltage boost which is proportional to the magnitude and power factor of the through current, right, because Q C is equal to I square X C. So, main purpose of the series capacitor is that it actually its main purpose is or primary objective is to increase the your voltage level of the network, right. And as you know that though not much, it also reduce the power losses, because we have in the load flow studies the power loss equation we have seen that your what you call power loss, just in general I am writing power loss is equal to R in general P square plus Q square divided by voltage square. This we have seen, this is the power loss, right, this is the P loss, and Q loss is equal to X into the same thing P square plus Q square upon voltage magnitude square. This is the power loss equation, and because of the series capacitor placement in the line, that voltage is improving. If the voltage improves, although this thing is unchanged, right, all this only little due to the improvement of the voltage, there will be a power reduction in power loss, but that is quite less, right, that is quite less, but though not much, it improves the your what you call it reduce the power losses, because its voltage is getting improved, right. Because suppose for example, suppose without series capacitor, for example say without series capacitor, right, suppose your voltage was V was say magnitude was 0.95 per unit, right. So, when suppose and with series capacitor, say with series capacitor, suppose when you put the series capacitor, say it is becoming 0.98 per unit, suppose voltage has improved. So, as soon as this voltage is improved, basically the numerator is increasing, right. So, that means compared to this one, then what will be the your just for your sake of understanding, suppose this one suppose P loss, or let me write you in a better fashion such that understand your concept will be clear. Suppose this is P loss, just for your understanding, without your series capacitor, I am making SC series capacitor is equal to say only one R into P square plus Q square upon magnitude V square, right. Similarly, say P loss with series capacitor, SC means series capacitor, say R into P square plus Q square upon your say due to the capacitor voltage, now we are making say Vc, same voltage, the same node, but instead of this thing Vc. Now, if you divide this, suppose this is your equation 1 and this is equation 2, suppose 2 divided 1, equation 2 divided by 1, then we P loss, that is with series capacitor, not shunt capacitor, it is series capacitor, right, divided by P loss without series capacitor, you just divide it, it is with series. So, R into P square plus Q square upon Vc square into V square divided by R into P square plus Q square. So, this will be cancelled, right. That means your P loss with series capacitor divided by P loss without series capacitor is equal to your V square upon Vc square, right. Therefore, P loss with series capacitor, P loss with series capacitor is equal to magnitude of V square by magnitude of Vc square into P loss without series capacitor, right. So, if your, for example, suppose if it is, if before series capacitor, if it is V is equal to say 0.95 per unit, and suppose after placing capacitor say 0.9 per unit, right, that means your V square upon V c square from this equation only, it is actually, it will be 0.95 square divided by 0.98 square, right. So, that is actually 0.95 by your 0.98, right. That is your what you call P loss without series capacitor, with series capacitor, and P loss without series capacitor. So, just a minute, P loss with series capacitor, actually it is V c, sorry, this is your P loss with series capacitor is equal to this one into this one. So, it is V square upon V c square, yes. So, if you take that V c is 0.9, V c is equal to your 0.98 and V square is equal to this thing. So, you can find out what will be your P loss with series capacitor. So, in that case what will happen, this is square, actually this is square, right. So, whenever you put that your series capacitor, because the voltage is improving, right, voltage is improving. So, naturally your what you call that this power loss will because of the improved voltage, because it is your much less. So, power loss will be higher, it is much smaller, much improved. So, it will be square will be also less. So, power loss will what you call will decrease to some extent because of this your what you call that voltage improvement. So, initially it was 0.95 say per unit you have taken, and now after the series capacitor voltage magnitude has changed to 0.98. So, V square upon V c square, right. Now, as soon as you put it, therefore, this thing, this will be, that means this equation can be written as P loss without series capacitor, right, is equal to V c square upon your V square, right, into P loss without series capacitor. So, whenever you put this one, whatever will be there, that your what you call that your power loss will not do much, but because of the improvement of the your voltage, it will what you call, it will increase for right. For a simple case, right, another thing, for example, suppose V is equal to, we have taken 0.95 per unit, for example, suppose V c is equal to 1.0. So, in that case, for purpose of explanation, if V c is equal to 1.0, it will be R into your P loss without series capacitor will be, if V c is 1, R into P square plus Q square. But if it is 0.95 say, so it will be approximately 1.055 something. If you take V is equal to your 0.95 square, so it will be not 1.055, it will be your 1.05 roughly, it will be your 1.099 something it will come, right. So, that means without series capacitor, the R into P square plus Q square is multiplying by this much, it is higher. But if it is suppose V c is raised to 1, so it will be just R into P square plus Q square. So, with series capacitor, that your loss will decrease. So, that way, that means whatever P loss with series capacitor and without series capacitor, right, whatever it was there, so P loss with series capacitor by P loss without series capacitor. So, it is R into P square plus Q square upon V square into V square upon R into P square. So, these two will be cancelled. So, it is coming actually V square upon V c square. So, this way that your what you call that loss your what you call the loss will decrease, and simple expression is maintained, the P loss is proportional to your what you call with series capacitor V square upon V c square into P loss without series capacitor, right. So, P loss without series capacitor, you whatever you have, you put it there. So, you will find that approximately that to some extent it reduce the losses, right. Thank you very much, we will be back again.